Welcome! In this session, we'll tackle problem number 1880, check if word equals summation of two words. This is an interesting problem that combines string manipulation with numerical operations. Let's explore the problem, understand its requirements, and discuss the best approaches to solve it. So, let's dive in. In this problem, you are given three strings, first word, second word, and target word, all consisting of lowercase English letters. The goal is to determine if the summation of the values of first word and second word equals the value of target word. Here, the value of a word is calculated by treating it as a base 10 integer, where each letter is replaced with its position in the alphabet, starting from 0. For instance, the letter A corresponds to 0, B to 1, and so on up to Z, which corresponds to 25. The word itself is then interpreted as a number in base 10. For example, ABC becomes 012, which is equivalent to 12 in base 10. The task is to return true if the sum of the values of first word and second word matches the value of target word, and false otherwise. To clarify how the output is determined, the problem requires returning true if the integer representation of first word added to the integer representation of second word equals the integer representation of target word. If this condition is not met, you return false. Let's look at some examples to better understand the process. In the first example, the input is first word equals ACB, second word equals CBA, and target word equals CDB. The output is true. Here's why. The value of first word, which is ACB, is determined by converting each letter to its respective position in the alphabet. A becomes 0, C becomes 2, and B becomes 1. This gives us the number 021, which is 21 in base 10. Similarly, second word, CBA, becomes 210 in base 10. Finally, target word, CDB, becomes 231 in base 10. Adding the values of first word and second word, we get 21 plus 210, which equals 231. Since this matches the value of target word, the output is true. Now consider another example, where first word equals AAA, second word equals A, and target word equals OB. In this case, the output is false. Here, the value of first word, AAA, is calculated as 000, which is 0 in base 10. Similarly, second word, A, also converts to 0. For target word, OB becomes 001, which is 1 in base 10. Adding the values of first word and second word, we get 0 plus 0, which equals 0. This does not match the value of target word, which is 1, so the output is false. In another example, where first word equals AAA, second word equals A, and target word equals AAA, the output is true. In this case, the value of first word, AAA, is 000, which is 0 in base 10. The value of second word, A, is also 0. Finally, the value of target word, AAA, is 0000, which is also 0 in base 10. Adding the values of first word and second word, we get 0 plus 0, which equals 0. Since this matches the value of target word, the output is true. The constraints for this problem include ensuring that the lengths of all three strings are between 1 and 8 characters, and that they consist only of lowercase English letters. It's important to consider cases like strings with leading zeros, single-character strings, and the maximum length strings to ensure your solution handles all edge cases correctly. To solve this problem, let's first consider a brute force approach. The intuition here is straightforward. We directly convert each string, first word, second word, and target word, into their respective numerical values. This conversion is based on mapping each letter from A to Z to digits 0 through 25. For instance, the string ABC corresponds to the digits 012, which, when treated as a base 10 number, becomes the integer value 12. Once these conversions are done, the solution simply checks whether the sum of the numerical values of first word and second word matches the numerical value of target word. The conversion process involves iterating through each character of the string, so the time complexity to convert a single string is O(m), where m is the string length. Since we perform this conversion for all three strings, the total time complexity becomes O(n), where n is the combined length of all three strings. This approach is efficient in terms of time complexity for this problem. While the brute force approach is already optimal in terms of time complexity, there is room for improving the implementation to make it more concise and readable. The chosen strategy retains the same core idea but focuses on simplifying the conversion process. We define a helper function called convertToNumber that converts a given string into its numerical value. This function works by iterating through each character of the string, converting it to its corresponding digit using the formula ord, char, ord, and then concatenating these digits into a single string, which is finally converted to an integer. Using this helper function, we efficiently compute the numerical values of first word, second word, and target word. The final step is to check whether the sum of the first two values equals the third. This approach leverages Python's built-in string manipulation and integer conversion features to streamline the process, making the implementation cleaner and easier to understand. One key observation in this problem is that we are essentially working with a custom base 26 numbering system, where each letter represents a digit from 0 to 25. By leveraging Python's capabilities to handle strings and integers, the solution becomes both concise and efficient. The time complexity remains O(n), where n is the total length of all strings combined, as we still process each character exactly once. The space complexity is O(1) additional space, aside from the input strings themselves. This approach stands out for its simplicity and clarity. While alternative methods, such as manually computing digit values without string concatenation, can achieve the same result, they often lead to more verbose code and are more prone to errors. By contrast, the chosen strategy strikes an ideal balance between readability, maintainability, and performance, making it the most effective solution for this problem. This problem highlights the power of applying simple mathematical observations and efficient string manipulation techniques in programming. The chosen approach demonstrates how to solve the problem optimally while maintaining a clear and concise coding style. By mapping letters to digits and treating strings as numbers in a custom base, we arrive at a solution that is both elegant and efficient. This reinforces the importance of leveraging built-in language features to simplify implementations without sacrificing performance. Overall, this problem serves as a great exercise in combining foundational concepts with practical coding techniques to arrive at a clean and effective solution. In this problem, we are tasked with checking if the summation of two words equals a third word, based on a specific mapping of characters to numbers. Each string, first word, second word, and target word, represents a number where each letter corresponds to a digit. Specifically, A maps to 0, B maps to 1, and so on, up to Z, which maps to 25. To solve this, the first step is to define a mapping function. This function will translate any character from A to Z into its corresponding numerical value using the formula ord, char, ord, a. For example, A becomes 0 since ord, a equals 0, and C becomes 2 because ord, C, ord, a equals 2. This mapping is a fundamental part of the solution since it allows us to efficiently convert the letters in the words into their numerical equivalents, which we can then use for arithmetic operations. After defining the mapping, the next step is to convert each string into its corresponding numerical value. To do this, we iterate through each character in the string, map it to its numerical value, and then use place value calculations to construct the final number. Each character's numerical value is multiplied by its place value, which is determined by powers of 10, and these are summed to get the complete number. For instance, given the string ABC, A maps to 0, B maps to 1, and C maps to 2. The numerical value is calculated as 0*10 squared plus 1*10 to the power of 1 plus 2*10 to the power of 0, which equals 12. Once the string's first word, second word, and target word are converted into numbers, the next step is to add the numerical values of first word and second word, and compare the result to the numerical value of target word. If they are equal, we return true. For example, if first word is ACB with a value of 21, second word is CBA with a value of 210, and target word is DBB with a value of 231, we check if 21 plus 210 equals 231, which it does, so the result would be true. To ensure the algorithm works correctly in all scenarios, we need to address edge cases. For instance, if any of the input strings are empty, we return false, as no valid numeric value can be formed. For single character strings, we need to ensure the mapping function properly handles these minimal cases. Additionally, the algorithm should be designed to handle large strings efficiently, avoiding issues like integer overflow when the numerical values become very large. There are also some key insights to note about the algorithm. First, the mapping function using ord, char, ord, ensures constant time conversion for each character, making it highly efficient. Second, the place value calculation ensures each string is correctly converted into a number by iterating left to right and multiplying by the appropriate power of 10. The algorithm is robust for strings of varying lengths and values, and its time complexity is O(n), where n is the total number of characters across all strings. Space complexity is minimal, as we use only a few temporary variables and no additional data structures beyond the inputs themselves. Now, let's walk through a concrete example to reinforce the process. Suppose we have first word equals ACB, second word equals CBA, and target word equals DBB. First, we convert first word. The mapping gives A equals 0, C equals 2, and B equals 1. Using place value calculations, the numerical value is 0*10 squared plus 2*10 to the power of 1 plus 1*10 to the power of 0, which equals 21. Next, we convert second word. Here, C equals 2, B equals 1, and A equals 0. The value is 2*10 squared plus 1*10 to the power of 1 plus 0*10 to the power of 0, which equals 210. Finally, we convert target word. The mapping gives D equals 3, B equals 1, and B equals 1. The value is 3*10 squared plus 1*10 to the power of 1 plus 1*10 to the power of 0, which equals 231. We then check if 21 plus 210 equals 231, which it does, so the result is true. To optimize the algorithm, we can avoid explicitly calculating powers of 10 by directly manipulating strings during the conversion process. This reduces computational overhead. The time complexity remains O(n), and space complexity stays at O(1), making the solution both efficient and scalable. The solution defines a class solution with a method isSumEqual that takes three string inputs, first word, second word, and target word. The goal is to check if the numerical sum of the first two words equals the numerical value of the target word. A helper function word2number is defined to convert each string into its numerical representation. This is achieved by converting each character in the string to its relative position in the alphabet, A equals 0, B equals 1, Z equals 25, and concatenating these digits to form a number. The method then computes the numerical values of the three strings and checks if the sum of the first two equals the value of the third. If true, it returns true, otherwise, false. This implementation is efficient and concise, handling edge cases such as strings of varying lengths and empty strings. This is the Java implementation of LeetCode problem number 1880, check if word equals summation of two words. The logic mirrors the provided Python solution, converting words to their numerical values by interpreting each character as its alphabetical index, A equals 0, B equals 1, Z equals 25. The solution then checks whether the sum of the first and second word's numerical values equals the target word's numerical value. Key differences in Java include explicit type declarations, the use of a string builder for performance while building numerical strings, and Java-style class structure. In this example, we are tasked with determining if the sum of the numerical values of first word and second word equals the numerical value of target word. To do this, each letter in the string is converted into its position in the alphabet starting from 0, or A is 0, B is 1, and so on. For the word ACB, we break it down letter by letter, A maps to 0, C maps to 2, and B maps to 1. These values are then combined to form the string 0201, which is interpreted as the integer 201. Thus, the numerical value of first word is determined to be 201. Now, we convert second word, which is CBA, into its numerical value. For each letter, C corresponds to 2, B corresponds to 1, and A corresponds to 0. When these values are combined, they form the string 210, which is then converted into the integer 210. This gives us the numerical value of second word as 210. Next, for target word, which is CDB, we repeat the same process. C maps to 2, D maps to 3, and B maps to 1. Combining these gives the string 231, which translates to the integer 231. Therefore, the numerical value of target word is 231. After calculating the numerical values of all three words, we proceed to check if the sum of first value and second value equals target value. For this example, we calculate 201 plus 210, which equals 411. Comparing this result to 231, we find that 411 is not equal to 231. This means the answer for this example is false. Moving on to the next example, we start with first word as AAA. Here, each maps to 0, so combining these gives the string 000, which translates into the integer 0. Therefore, the numerical value of first word is 0. For second word, which is a, we follow the same process. The letter A maps to 0, forming the string 0, which converts to the integer 0. This makes the numerical value of second word equal to 0. Then, for target word, which is AAA, each again maps to 0. Combining these values gives the string 0000, which translates to the integer 0. As a result, the numerical value of target word is also 0. At this stage, we check if the sum of first value and second value equals target value. Calculating 0 plus 0 gives 0, which is indeed equal to 0. This means the result for this example is true. In the next example, first word is again AAA. Following the same conversion process, each maps to 0, forming the string 000, which becomes the integer 0. Hence, the numerical value of first word is 0. For second word, which is ABC, each letter is converted as follows: A maps to 0, B maps to 1, and C maps to 2. Combining these values forms the string 012, which translates to the integer 12. This gives us the numerical value of second word as 12. Similarly, for target word, which is ABD, the letters convert to A as 0, B as 1, and D as 3. Combining these gives the string 013, which becomes the integer 13. Finally, we check if the sum of first value and second value, which is 0 plus 12, equals target value, which is 13. Since 12 is not equal to 13, the result for this example is false. To understand the time complexity of the solution, we begin with the word-to-number function, which converts a word into its numerical representation. For a word of length n, this function processes each character individually. Calculating the numerical value of a character, using operations like ord, char, ord, takes constant time, or O1. Next, the join operation concatenates these characters into a string, which requires O(n) time since it involves processing all n characters. Finally, converting this string to an integer using the int function also takes O(n) time, as it depends on the length of the string. Combining these steps, the overall time complexity of the word-to-number function for a single word is O(n). Now, the word-to-number function is applied to all three input words, first word, second word, and target word, which have lengths n1, n2, and n3, respectively. For first word, the function takes O(n1) time. Similarly, it requires O(n2) for second word and O(n3) for target word. Adding these together, the total time complexity for processing all three words is O(n1 plus n2 plus n3). Following this, the solution checks if the sum of the numerical values of the first two words equals the numerical value of the target word. This involves a simple addition and comparison operation, which both take constant time, or O1. Therefore, the dominant factor in the overall time complexity is the conversion of the words to their numerical values, resulting in a final time complexity of O(n1 plus n2 plus n3). The space complexity of the solution is influenced by the word-to-number function and the additional variables used. Within word-to-number, the join operation creates a new string of length n, requiring O(n) space. Converting this string to an integer with the int function also uses space proportional to the number of digits, which corresponds to O(n). Hence, the space complexity for processing a single word is O(n). When the function is applied to all three words, the space is not cumulative because the memory used for each word is released once the function completes. Instead, the peak space usage depends on the longest word among the three inputs. Additionally, other variables, such as those storing the numerical values and the result of the comparison, use a constant amount of space, or O1. These factors combined lead to a space complexity determined by the longest word, which is O max n1, n2, n3. In summary, the overall space complexity of the solution is O max n1, n2, n3, driven by the memory required to process the longest word among the three inputs. Comparing this with a naive approach helps illustrate the efficiency of the current solution. A naive method might involve summing the ASCII values of the characters directly, but this would require additional logic to account for the positional significance of characters. For example, the word ABC does not represent the sum of its characters' ASCII values but rather the number 012 when treated positionally. While the naive approach would still have a time complexity of O, N1 plus N2 plus N3, due to character iteration, handling positional significance would add more computational overhead. In contrast, the optimized approach in this solution uses string manipulation and arithmetic to achieve the desired functionality with minimal complexity. The time complexity of O, N1 plus N2 plus N3, and space complexity of O, max, N1, N2, N3, are not only efficient but also optimal for the problem requirements. The solution performs consistently across all input scenarios, making the time complexity O, N1 plus N2 plus N3, the same for best, average, and worst cases. This is because the solution processes every character in the input words regardless of their contents. There are no shortcuts or early exits. Mathematically, since each character requires O1 time to process and there are N1 plus N2 plus N3 characters in total, the overall time complexity is proportional to this sum. Similarly, the space complexity depends on the longest word, as the word-to-number function processes one word at a time, and intermediate results are discarded after each function call. This leads to a space complexity of O, max, N1, N2, N3. These analyses confirm that the solution is both efficient and well-suited to handling the constraints of the problem. When solving this problem, there are a few common pitfalls to watch out for. First, one of the biggest mistakes involves the string-to-number conversion process. Remember that the ASCII value of A is 97, but for this problem, A needs to map to 0. If you forget to subtract the ASCII offset, you'll end up with incorrect numerical values, which can make your solution fail even if the rest of your logic is sound. Another common issue is mishandling leading zeros. For example, if a string starts with of which represents 0, you need to ensure that this doesn't create invalid numbers like 012, which isn't allowed in most contexts. Instead, it should represent 12. Lastly, edge cases are often overlooked. For instance, you might encounter strings of different lengths or scenarios where the target word is smaller than the sum of the first two words. These edge cases can be tricky, and failing to account for them can introduce subtle bugs that are hard to detect during testing. Now let's consider two more areas where mistakes often occur. An inefficient implementation is a frequent issue. For example, using nested loops to check combinations might seem like an easy solution, but it can result in a time complexity of O, n squared, or worse, which doesn't scale well for larger inputs. While this might work for small test cases, it's a performance bottleneck for real-world scenarios. Another problem arises from mishandling constraints. Sometimes, developers assume that strings will always be short or that inputs will always be valid. Ignoring constraints like maximum string lengths or edge cases can lead to runtime errors or unexpected behavior. It's critical to always align your implementation with the given constraints to ensure a robust solution. In interviews, this problem can provide valuable opportunities to demonstrate key problem-solving skills. Recognizing patterns is essential. This challenge is essentially about converting characters to their numerical equivalents and performing basic arithmetic. By identifying this relationship early, you can simplify the problem significantly. It's also important to clarify assumptions during discussions. For instance, confirm whether leading zeros are allowed, whether inputs are guaranteed to be valid, and the maximum length of the strings. Once you have a basic solution, focus on optimizing it for scalability. Instead of brute forcing, explore direct mathematical operations that improve efficiency. Furthermore, don't wait for the interviewer to ask about edge cases, proactively bring them up. Discuss scenarios like empty strings, leading zeros, or very large inputs, and explain how your solution handles them. Finally, reviewing related problems, such as add binary or add strings, can help you prepare for variations of this question. To wrap up, let's review some alternative approaches to solving this problem. The brute force approach is a straightforward starting point. It's simple to implement and can help you build intuition for the problem. However, it's inefficient for larger inputs due to its high time complexity. A more optimized mathematical approach involves converting strings to numerical values in one pass using a single loop. This method is much faster, with a time complexity of O(n), where n is the total length of all strings. However, it does require careful handling of edge cases, which can make it slightly more challenging to implement. Another option is using hashing for fast lookups. By pre-computing numerical values for common substrings, you can make repeated queries more efficient. However, this comes at the cost of higher space complexity, and it may not be applicable to all variations of the problem. Each approach has its pros and cons, so choose the one that best fits the constraints and requirements of the problem you're solving. Great job! To wrap up, we reviewed the problem, broke it down, and explored a solution. Remember, practice is key to mastering these concepts. Thanks for joining, and don't forget to like, subscribe, and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!